Well, thanks, guys. I appreciate you joining us today. We're very privileged to have the man himself, Dan Knighten, joining us from Audio Precision and down in Portland. Dan was the brainchild behind the 517 and where it's taking Audio Precision with its business. So we're excited to have him take us through that and do some PDM microphone testing as well. My name is Jeff. I'm with GerrAudio. We look after AP here in Canada. On this call today, we have John Whaling as well. John might wave there if he's listening. He's our broadcast and AP specialist within the company. And we also have Peter, who works with me in Ontario, and Sean out west, and Bob, our fearless leader there as well. So we're excited to have you all here today, and wanted to make that quick introduction before we hand it over to Dan. And I will let you know that this is fairly informal. We've got a reasonable crowd today, but don't hesitate to let us know if you have any questions. We want this to be as friendly as possible for us Canadians today. So just let us know, or let me know if you have any questions, and we can certainly stop and go off in a different direction. And this is going to be the first of two presentations. We're going to be doing another one on Bluetooth testing using the 517 as well. So we'll be providing some dates on that, but it'll be a couple of weeks from now. So without any more, I'm going to hand it over to Dan.
All right. Thank you very much, Jeff. Let me now re-find my screen to share. Okay, so I hope everybody can see my PowerPoint presentation. The modern era is quite interesting because I'm actually sitting in my one-bedroom apartment making a presentation live into Canada while remote controlling an analyzer that's actually some 20 miles physically away from me. So it's to some extent kind of amazing that all of this technology works. But as Jeff mentioned, we can keep this pretty informal. The last presentation I did on this was had a couple hundred participants, and we had to mute them in mass and then have people submit questions. But maybe there is one person who should mute their microphone. But for everybody else, if you have a question, please feel free to unmute yourself and just ask the question. We don't have to stand on that formality here. And what I want to go through today is, the intersection of a few different things. We have brought a new analyzer to market, and that analyzer has all the bits and pieces to be functionally optimized for measuring electroacoustic devices. And so that kind of is our impetus for putting this together. But most of what we'll talk about in this meeting is not specific to the APx517. In fact, a lot of it isn't necessarily specific even to using an audio precision analyzer. I'll just go through the considerations we have and need to accommodate when we want to measure a MEMS microphone. And at a certain level, we're really just talking about, hey, how do we measure a microphone? So I will talk about the 517 specifically. I'll talk about our interfaces for talking to PDM devices, but then I'll go through some higher level considerations in terms of how we're going to physically do this test and what are the prerequisites for that. We'll talk about software configuration inside of the APx500 software and the various steps we'll go through to configure our setup to make those measurements, and then we'll make some measurements. And I'll pause at the end for any questions you may have, but again, as we go along, feel free to ask. Okay, so what is the 517? The 517 is just, it's another tool. I have spent over 20 years of my life making different gray boxes, and I really love them and get very excited about them, but I realize not everybody cares about audio analyzers as much as I do. But what I wanted to do with the 517 was make a single box that would bring together everything you practically need when you're testing a speaker, a microphone, a headphone, or a headset. Sort of generically what we would call electroacoustic transducers. So on the left side there where you see two speak-on connectors, behind those two connectors is a 35-watt mono power amplifier. So there are two connectors, and I should disambiguate that. To a great deal, we've optimized this box also for use on production lines. And one thing that can be useful on a production line is there's some amount of time when you're testing a device, which is just putting the device in a test fixture and removing it from that test fixture. So part of the design here is you could actually share one analyzer between two test cells and ping pong back and forth. So they're two power amplifier output connectors, but they're really just switchable connectors to one mono power amplifier. That power amplifier has a voltage rail at 17 volts, and we can drive into a 2 to 16 ohm load. So we do actually have a little bit more than 35 watts available. The current limit is really going to restrict you into what you can go in, but we can deliver at least 35 watts into that impedance range. It's a pretty nice power amplifier, better than minus 90 dB THD plus N. And really one key thing is we have worked pretty hard to make it so that if you goof things up, you can't blow up the analyzer. So we're of course output current limited, but every now and again, somebody connects the output of one power amplifier to the input of another power amplifier. I won't try and explain how that happens, just believe me, it does happen. So we've protected it against being back driven, and we've protected it to very high voltages. And the other thing we've done is we've built the impedance sense function directly into the power amplifier. So we're detecting the current right in the feedback loop of the amplifier. And the other thing we're doing is on the speak-on connectors, those are actually 4 poles, and we're using 2 of the wires to send the current to the speaker driver, but we're using the other 2 wires to detect the actual voltage at the terminals. That gives us a so-called Kelvin impedance measurement. From left to right on that front panel, the next thing we have is a 2-channel. So this is a stereo headphone amplifier. You may or may not be able to tell that there are a couple thumb screws on the thumb panel, sub panel there, and you can switch this out for a 1/4 inch or an 1/8 inch, or even you can get a little panel that just has 2 BNC outputs. That's got a 9-volt max output, and it will drive into 2 to 800 ohms. And it's got the same built-in current sense function. And one other thing I'll say about current sense and impedance measurement is the vast majority of headphone amplifiers have a few ohms of source impedance, and that source impedance varies versus frequency. If you go to measure the impedance on a headphone driver and you do that via the very typical solution of using a current sense resistor and then working backwards with Ohm's law, you get into the situation was, that almost always assumes, I shouldn't say almost always, that always that I have ever seen assumes that your amplifier has 0 ohm source impedance. Nobody ever puts the amplifier source impedance into the equation. And if that source impedance varies with frequency, it's even harder to do that. So nobody does. And so then if your amplifier is a typical power amplifier, well, those guys typically do have a source impedance pretty darn close to 0. So it's not typically an issue. But with headphone amplifiers, it's not typically 0. And so you do see, unfortunately, a lot of impedance plots published for headphone drivers that are wrong. So one of the things we put effort into is our headphone amplifiers a lot more like a power amplifier in the sense that its source impedance really is very close to 0. On the analog input side, the most notable thing is really that we've built in microphone power for measurement microphones. So ICP, IEP, CCP, Deltatron, every variation you've seen or heard on constant current DC bias microphones for 10 milliamp. Now, the other thing you can do is flip that over and just provide a constant voltage bias, and that's software selectable between 0 and 12 volts. And on the XLR connectors, we do provide 48 volt phantom power. Now, one thing that, AP is not the first company to have the idea of why don't we put all the bits and pieces you need to measure a speaker in one box. I would say that we've executed it better in a lot of the details, but one area where we've, I think, really done something different is we have a wide variety of interface modules for different digital interfaces. And on the 517, there's a module slot that will accept any of our existing modules. So now if you're testing a Bluetooth headset, or you're testing a PDM microphone, or even something at the circuit board level with I2S, that can all be pretty easily accommodated. So moving on, one area that can be a little confusing is AP currently sells 2 different modules that provide a pulse density modulation interface. We have our older PDM module and we have our newer PDM16 module. And they do some slightly different things, so we continue to sell them. But in terms of figuring out which one is right for you, kind of broadly speaking, the question is you need to test more than 2 inputs at a time. So our PDM module has 1 data line coming in. You can multiplex 2 microphones or 2 other PDM channels onto that. Our PDM16 module has 8 data lines and can therefore measure up to 16 microphones simultaneously. Now, one other thing that we decided to explicitly accommodate is it's not awesome trying to shove your APX analyzer chassis into your anechoic chamber. So on the PDM16, it actually uses a remote pod that can be placed up to 10 meters away from the chassis of the analyzer. On the PDM, we don't have a remote pod. We do have an accessory product we sell, which is a line driver, which somewhat accommodates the same use case, but it's not quite the same. But there are some other details. So on PDM, we have a function that lets you directly measure power supply rejection ratio measurements. That function is not available on PDM16. The PDM module has a lot more flexibility in terms of decimation rates, whereas PDM16 is pretty strictly just the power of 2 decimation rates. PDM also has the ability to induce or measure jitter on your PDM clock signal. And then right at the top, on PDM, it has a PDM generator function as well as an input. The PDM16 is an input only. One way of summarizing it, we really optimize PDM16 for people who need to measure arrays of PDM microphones. So, of course, with the huge popularity of smart speakers, more and more we're seeing devices that have, need to measure 6, 7, or more PDM microphones simultaneously. Or if you're doing production tests of naked PDM microphones, it's useful to just be able to test a whole bunch of them at a time. So I would say that would be the primary driver of PDM16 over PDM. And one thing I'll say generically is we very often assume when somebody says, I'm testing a MEMS microphone, that they're testing a MEMS microphone with a pulse density modulation output. That is not a universally true statement. There are MEMS microphones that have analog outputs, continuous analog voltage outputs. There are MEMS microphones that have I2S outputs. So while in this presentation I'll be talking, and what I have as a sample device is an array of MEMS microphones with PDM outputs, vast majority of what I'll talk about will apply to any, really any microphone, where we don't care particularly about what the physical sensor is. So one general topic I want to touch upon is our test chamber considerations. This is something where Audio Precision has a long history in electronic tests. And one of the things that's frankly convenient about electronic tests is it doesn't make any noise. But when we're testing an acoustic device, and especially a microphone, we have to have the physical environment in which we're testing the microphone. We have to give a thought to that. And the gold standard for this is to have an anechoic test chamber. We all wish we had one. Very few of us do. And those of us who do, it's seldom as large as we'd like. And the issue here is that the smallest frequency in which a given space can be anechoic is proportional to the size of that space, or really to the wavelength of that frequency. And if we want to get down to 20 hertz, the requirement is awful, because at that point we're talking about having a chamber which has a smallest dimension in the range of 10 meters. So even a good sized anechoic chamber, such as the one pictured, is good to 200 hertz, maybe 100 hertz. Getting below 100 hertz is difficult. For many of the measurements we're going to make on a microphone, however, we can probably get away with something considerably smaller, particularly if we are testing a naked microphone. That is to say, something like just a MEMS microphone chip on an eval board, not installed in a finished product. What's pictured in the center of the slide here is actually a box that is designed primarily for testing hearing aids, but it has extremely good isolation or insertion loss. So it does a really good job of excluding ambient noise from your measurements. And it is actually pretty free of internal reflections, above 200 hertz, maybe above 400 hertz is really good. So particularly if we're testing a small device or a naked microphone and we're concerned mostly with voice passband, it can work quite well. And what I'll be using today is a much hokier setup. I call this the half space. So what I have is my circuit board with my array of MEMS microphones just sitting on a tabletop surface. On the same surface, I have my speaker that I'm going to be used for stimulating the microphones as well. It is not an ideal setup, but I'll show you it is actually possible to make real measurements in this setup. And we're taking advantage of the fact that our device under test is basically flat. So the microphones are sitting very close to the surface. I realize in the picture there's a 1/2-inch microphone, but I'm actually using a 1/4-inch microphone. So it the reference microphone minimally impacts the acoustic space. And the effects of a half space on a speaker are to double the apparent sound pressure. And since we're not making measurements on the speaker, we're making measurements on that microphone, that's actually going to help us out. It's going to give us more sound pressure at the point of test for a given speaker than we would have otherwise. Okay, now the other part we're going to look at is what do we use as a sound source. So we're measuring a microphone. We need something that's going to provide the actual test signal. And one of the challenges is, this might be a flippant statement, but there is no such thing as a measurement speaker. There is such a thing as a measurement microphone, and a measurement microphone is really just a microphone that is optimized to provide a flat frequency response and operate in a certain type of acoustic space, for example, a free field or a pressure field. But for our sound source, we have to pick something, and we're going to pick something and then work with it. This is a pretty broad range of things to look at, but a classic solution that you'll see quite a bit is people will use a mouse simulator. A mouse simulator has a couple advantages. First of all, mouse simulators are often, if not, I'll just say always, well-behaved speakers. And what I mean by well-behaved is that they don't have a flat frequency response, but they don't have any very sharp nulls or peaks in their response, and that makes it possible to equalize. And the thing that's, I'll say, drives a lot of use of mouse simulators is their various electroacoustic and telephony measurement standards that are based around using a mouse simulator in a specific geometric relationship to the device under test. And so, for example, if you're making a smart speaker that somebody can use as a speakerphone and you decide, oh, I'm going to test it to an ITU standard, well, that ITU standard is going to call for making the measurement, and it actually specifies the size of a table to use and where to position things, and it's going to specify the use of a mouse simulator at a specific geometric relationship to the device under test. If you are not making measurements to one of those standards that requires the use of a mouse simulator, then you have quite a bit more flexibility. And now it really fundamentally comes down to the frequency range that you're going to measure your microphone over and what sound pressure you want to be able to achieve. And that last part might be the more critical of the two. If you want to drive your microphone, if you want to discover your microphone's overload point, some MEMS microphones, their overload point, I'll say, might be as low as 120 dBSPL, but some of them might be as high as 140 or even higher. I know some companies are pushing that boundary. And finding an honest speaker that can really generate a continuous signal at those kinds of sound pressures is not easy. Or perhaps it is easy, but it's not cheap. And then in addition to that, you want it to be able to reproduce that sound pressure level over the frequency range that you want to test your microphone over. And then it becomes really challenging because every now and again somebody says to me, I want to test my microphone to its overload point from 20 hertz to 20 kilohertz. And it's sort of like, so you want a speaker system that'll produce 140 dBSPL from 20 hertz to 20 kilohertz. I mean, that is something you can buy, but it's a very, very impressive speaker system. And I'll show you what I mean by this, but then the other thing that you want in that speaker system is, again, it doesn't have to be a perfectly flat frequency response. We can apply equalization to the speaker, but generally speaking, you cannot equalize resonances. So if you have a resonance in a speaker, you keep putting more energy into the resonance and it keeps canceling itself. So in terms of the frequency response, what I like to see in a speaker I'm going to use for microphone measurements, it doesn't have to be perfectly flat, but I don't like to see any sharp features, essentially any resonances in the frequency response. And then what I'll actually be using for today's measurements, as you know, the shoemaker's children have no shoes. So I myself do not have any fancy speakers. I will be using this 3-inch single driver speaker. And it's a pretty reasonable speaker, but it's a $100 speaker. And I'll say a couple things. Single driver speakers are my preferred solution when measuring microphones because they're easier to position, right? When you have a multi-driver speaker and you're working in relatively close quarters, when you're working in the near field of the speaker as opposed to the far field, it's harder to position the speaker and not see artifacts at the crossover frequency. You don't have a crossover with a single driver speaker. However, what you do run into is you're not going to get a single driver speaker that works over a super broad frequency range. So again, the frequency range over which you want to make your measurements is extremely critical to think about. And then lastly, I'll reference measurement microphone. And this prerequisite is a bit of my own habit for how I measure other microphones. As you've just heard me belabor the challenges and difficulties of selecting a source speaker for your measurement, one way to sort of shortcut the whole thing is to measure your microphone by reference, or sometimes you'll hear the word substitution, to another microphone. And the beauty of that is you essentially remove your speaker from the equation. When you do microphone measurement by substitution, as long as there is some sound coming out of your speaker, you know, this doesn't work if there's nothing coming out of your speaker, but as long as there's some sound coming out of your speaker, what you're actually doing is dividing one microphone by another microphone, and that'll literally divide out the effects of your speaker. Now, what microphone to choose? Generally speaking, two ways to do substitution. You can either do them sequentially. So this is literally, you put the microphone you're measuring in a given physical location, you sweep it, then you remove it, and you substitute your reference microphone. Or simultaneous. In simultaneous substitution is my preferred solution because frankly, it is more convenient to just be able to play around with all your measurements as you go instead of constantly going in and out of your chamber and swapping things around. And in addition, when you do sequential substitution, you know, you have to be moderately careful to make sure you're physically putting things at the same location. The downside of simultaneous substitution is you can't physically overlap these things. And the measurement microphone is a physical object, and it is going to disturb the acoustic sound field. So for that and a couple other reasons, my preferred microphone when I'm measuring another microphone is a 1/4-inch microphone. It'll just physically have a much smaller body. And the other nice thing is that there'll be, not only will it disturb the acoustic sound field the less, but the 1/4-inch microphone will also give me a flat magnitude or frequency response all the way to 20 kilohertz, not quite regardless of its orientation to the sound field, but pretty close. A 1/4-inch free field microphone and a 1/4-inch pressure microphone have very similar magnitude responses. If you don't care about phase, we're done, and it's super easy. But particularly when we're measuring microphone arrays, we care about phase. So the other advantage of a 1/4-inch microphone, and one of the sort of weird things that we seldom talk about with measurement microphones, is a measurement microphone that has a flat magnitude response, say to 20 kilohertz. It is not going to have a flat phase response to 20 kilohertz. So this narrows me down into the 1/4-inch pressure field microphone. A 1/4-inch pressure field microphone has the flattest phase response of all within that 20 kilohertz bandwidth. And you notice that a lot of these things, frequency dependent, particularly if we're measuring a microphone that we're going to use in a voice band application like a smart speaker, maybe I only care about 100 hertz to 10 kilohertz. And that narrowing of frequencies makes the life of the measurement a lot easier. 100 hertz and up, the size of the environment that I need to make that measurement is a lot smaller. The challenges of finding a speaker that will generate the relevant energy is a lot easier. Going only up to 10 kilohertz means finding a measurement microphone that has a flat magnitude and phase response is going to be a lot easier. You know, everything gets easier. If somebody says, oh, I want a microphone that goes, you know, I want to test this microphone from 20 hertz to 20 kilohertz, that is a real challenge. I mean, that is just flat out a big physical challenge. It can be done. And frankly, from the measurement equipment point of view, it's not any more challenging. It's all these externalities that are going to be challenging. So this is a little bit of a rendition of the test setup that we're going to go through today. So exactly, I have everything plugged into my APx517, which is configured with a PDM16 module. So I've got the power amplifier driving a source speaker. I've got my 1/4-inch pressure field microphone plugged directly into my audio analyzer. And I've got a little eval board with 16 PDM microphones connected to our remote PDM input pod, which is then going all the way back to the analyzer. I just want to take a pause here and see if there are any questions so far. Okay. Oh, sorry. Let's jump into the software now. And so this is just what you'll see when you start up APx500. Now this is 6.0 software, and I'll be showing a few relevant features on that. But this is connected to our 517 right now. And we start in signal path setup. And my output connector is currently set to power amplifier. I'm going to go ahead and use that. Input, one of the things is a new feature as of 6.0 is the ability to have 2 inputs active simultaneously. I'll be taking advantage of that in a second here. But my first input I'm going to use for my analog measurement microphone. And I'm just using one channel for that. I am going to be using acoustic mode. that microphone is unbalanced or it's going into the BNC connector, I do need to provide it with power, so I'll go ahead and turn that on. And what I'm going to take advantage of the fact, because I am actually remote to this analyzer, is I'm going to grab the microphone's calibration data via the transducer electronic data sheet, or TEDS, which just reads that electronically. I'll go ahead and close that. And then I'll just bring up my signal generator, generate a sine wave out of our speaker, and verify that I am picking that up. Now I'm going to do a couple things here. First, I'm going to go back to my output side, and I actually want to calibrate this speaker. So I want to set the speaker so that instead of just feeding it volts, I know the acoustic sound pressure that it's generating. So I'll set my output in acoustic mode, and then I'll go to References, Output References, Acoustic, and I'm going to set my acoustic output level. And this is just a function to set that automatically for me. So I'll say, you know what, I want you to find me 1 Pascal. And, you know, I'm going to guess that it's probably somewhere between 100 millivolts and 3 volts. And so now that has, we would use the term regulated the generator so that I'm getting 93.98 dBSPL at 1 kilohertz. And now what you'll notice if I go back to verify connections is that I can set my signal generator in dBSPL, which is nice and handy. Now, what this has not done is this has set this really for this one frequency, and our speaker is not perfectly flat. So what I'm going to do is go ahead and add a measurement, and I don't need to be super fancy. I'll just add frequency response. So I'm going to go ahead and sweep the speaker. Let's go ahead and just sweep it full range just to see what it's like. We'll sweep it from 20 hertz to 20 kilohertz. Now the generator says 94 dBSPL. That will only be true. I only expect it to be true at 1 kilohertz, but we can start there. And so now we have the frequency response of this little 2.5-inch single driver speaker, which actually I'm pretty happy with. Now it does roll off rather quickly at low frequencies, which is not entirely unexpected. Now in truth, this speaker is meant to be a part of a little 5.1 system, so they have put a cap in it, so you get a very smooth roll off towards low frequencies. But, you know, if I look at this response, it's actually, you know, reasonably flat all the way up. Now, before I go to apply the speaker, if I try and equalize it, you know, at 80 hertz to match the output level at 1 kilohertz, you know, I'll be adding 30 odd dB, almost 40 dB to the signal. So that would blow up my speaker. So that's what I mean about what is the, you know, usable frequency range. And my, you know, my rule of thumb is to not try and equalize a speaker for sure more than 20 dB. And generally like 10 dB is kind of a healthy bit of equalization. So let's try this. Let's go 100 hertz to 20 kilohertz. And let's take our frequency response data, and let's just take the relative response. Let's export this. I'm going to go ahead and export all points. And we'll call this speaker FR. And now I'm going to go in my EQ function, and I'm going to say I want a relative EQ. And I'm going to re-import that data. And then I'm going to invert it. And select OK. And then for comparison, I'll just append graph data. So here we can see, just for reference, the equalized speaker response on top of the raw, or if you will, natural speaker response. One thing you can see is exactly above 200 hertz, we can get an extremely flat response out of the speaker. Below 200 hertz, it gets a little wonky. We can't linearly equalize it to a flat response, but it's actually still not terrible. I mean, we're still plus or minus 2 dB. Now, I'll show you in a few moments a sort of belts and suspenders approach to then measuring our microphones under test. But this is all the preparatory work. So we now have a reference measurement microphone set up and calibrated, and we've then used that reference measurement microphone to calibrate and equalize the sound source we're going to use to measure the microphones we're actually testing. So I'm going to go back to signal path setup. I'm going to go to input 2. Input 2, I'm going to select PDM16. And the default settings will actually work for us. And the default settings are x64, or in this case, it's input decimation, so it's 1/64 decimation. That gives us a decimated sample rate of 48 kilohertz and a bit clock rate of 3 megahertz. So this is sort of the most, 80% of the MEMS microphone applications out there are probably using these exact same settings. So a couple things. So now if we look at our input signal monitor, we have one that is monitoring our reference microphone input. And then we have the bottom one is looking at all 16 MEMS microphones on our little eval board. And if I go down here to add a new result, I'll say primary result, RMS level, and let's add it to PDM16. And so here we're looking at the 16 channels of data coming from the PDM microphones, as well as our reference mic simultaneously. And if I want, I'll just go back to my verify connections. I'll set my signal generator to 94 dBSPL. And I see a signal in the input signal monitor. And then in our measurement microphone. And then I see what is coming back from each of the MEMS microphones. And to some extent, or at some level, I have sort of an immediate check on sensitivity. because I'm generating 1 Pascal, and for example, on channel 1, I'm getting minus 24 dBFS. So I could say, oh, that microphone sensitivity is minus 24 dBFS per Pascal. Now, one thing to watch out for is my little tabletop test setup. The source speaker is quite close. It's only a handful of centimeters away from the array. So there's actually a material difference in distance from channel 1 to channel 16. So we have really intermixing, unfortunately, of two things, which is both the sensitivity and the variance in sensitivity in the capsules themselves. So like this particular capsule, the manufacturer says the sensitivity is minus 26 dBFS per Pascal plus or minus 3 dB. So, is number 16 really that much less sensitive, or is it really that much further? It's really a combination of the two. But I do have that sort of immediate readout and confidence here that things are all basically up and running. So now what I can do next is actually start making some measurements. So why don't I add acoustic response? And here's where I have to remember that, oh, wait a second, I've only calibrated my test speaker for 100 hertz on up. And I'll set the generator to 94 dB SPL. One other little detail I'll say about source speakers is ideally our speakers would be linear and time invariant. And if I find a voltage level that gives us a certain output sound pressure level, half that voltage should give us half that output. And that's what's assumed by the audio precision signal generator when I calibrate an acoustic output. For a good speaker, sort of inside of its operating range, that is a true statement. But I think we all know that speakers have compression. And I kind of recommend that you calibrate your acoustic output for the acoustic sound pressure you tend to use in your tests. And it wouldn't be a bad idea. So let's say you're going to do some of your tests at 94 dB SPL, some of your tests at 80, and some of your tests at 114 or higher, to have a separate signal path with a separate acoustic output calibration for each of those. Because even if the speaker's amplitude linearity is pretty flat, it probably will not have the same frequency response at differences in output of 10, 20 dB. So that's just a little aside on that. So I'm going to sweep from 100 hertz to 20 kilohertz at 94 dB SPL. I'm going to load up my previously captured speaker EQ.
Dan, it is possible to put that correction and the signal path setup too, is it not?
It is, and that's a very good question. So what Jeff is alluding to is here in the output signal path, I can specify my EQ as well. There is a subtle difference between when I specify an output EQ in the signal path versus when I specify an output EQ in the measurement, which is in the signal path, the EQ is implemented in real time by applying a 31 band bank of biquad filters to the signal before it goes out the connector. The advantage of that is it will provide an EQ for any signal you generate. The disadvantage of that is, it's finite precision. When we apply an EQ in the measurement knows exactly what kind of signal it's going to generate, and it will actually feed the EQ into the mathematical algorithm that synthesizes the test signal. And that lets us get an extremely accurate equalization function. So both are available. And frankly, maybe if you're looking for EQs that are plus minus a dB, it doesn't really matter which one you use. But if you want that really, really sharp, EQ that's going to be plus minus a tenth of a dB, then using the equalization function in the specific measurement you want to make works the best. So let's go ahead and sweep this. And I realize I'm probably going to run a little bit long. So if anybody has some questions they definitely want answered before they have to sign off the call, feel free to ask them now. Okay, so here's the impulse response of our measurement microphone. Here's the impulse response of all 16 MEMS mics, our energy time curve. Here is the frequency response as measured at the reference microphone. And this is great because it verifies for us that we got a good equalization on the speaker. And I can auto scale this to really zoom in, and we can see, particularly even at the worst, right, we're in a plus minus 0.2 dB kind of scenario here. So pretty darn good. So here's the frequency response of all 16 MEMS microphones. And you can definitely see you are going, or I shouldn't say you are definitely going to, but I'll say in my scenario, as those microphones get further and further away from the speaker, you do start to see like some wigglies here, which are a product of the fact that we've got a little circuit board. It does have bumps on it. It's not a perfect sound field. And then one that's interesting to look at is here's our delay. And what you may realize from the delay is there is a little error in the design of the circuit board, and the left-right data lines were actually inverted. So the microphone that is on the logical channel 1 is actually physically in position 2. But there you can see the delay. And then if we look at phase, it's interesting to look at input to output. And here you see beautifully the delay in time reflected in the phase of the 16 microphones. And group delay, just a little noisy. But you get your group delay, and on and on. Now let's look at a couple things. As I said, since we've calibrated our speaker and set it to generate 94 dBSPL, we can sort of read the sensitivity directly off this graph. In fact, I could do something like add derived result and say, and here is the measured amplitude from the frequency response at 1 kilohertz. And if we believe that the speaker was correctly calibrated to give us 1 Pascal, we're getting, somewhere between minus 24 dBFS to minus 30 dBFS per Pascal. Now, the other thing we have here is our reference microphone result. And to be very frank, reference microphones are more reliable than speakers. Simply, you have a much smaller diaphragm. The diaphragm's made out of usually a metal film, a metal foil. They tend to be much more stable in amplitude and temperature and humidity than any speaker. So what I can now also do is I'll take my reference microphone, I'll add a derived result, and we've added this new result called sensitivity. And I'm going to compare it to RMS level from PDM16. And now what I get is this is the dBFS, so that's our MEMS mic output per Pascal as measured by the reference microphone. And one thing that's nice about this is, let's say I do this sweep again. But I do it at 80 dBSPL.
Can you explain what that is actually doing? Is it basically subtracting the measurement mic from it?
It's subtracting it. Mathematically, it's really dividing it.
Right. So what is this showing us then at this point?
So what's handy about this is if I go look at the frequency response of the PDM mics, I lowered my stimulus level. So you notice the frequency response now, instead of being up at minus 24 to minus 30, is now at minus 36 to minus 45. But in the derived result, because I'm deriving this, the dBFS output of the MEMS microphones, by the sound pressure output of the measurement microphone, the sensitivity, which is the ratio of the two, hasn't changed. And in fact, I can totally go to town. Now I can even take out my EQ. And so this is getting at my earlier comment about one of the advantages of microphone substitution is you get out of being dependent on your source speaker. You're now dependent on your measurement microphone, but your measurement microphone is going to generally be more stable and more repeatable than any speaker. And the belts and suspenders approach is to just do both. I've calibrated this at 94 dBSPL, and I equalize it.
So would I be correct in saying that, these mics are, fairly linear, but they roll off in the high frequency, obviously above, 4K? Or is that a
Yeah,
positional thing? Would you?
there's some amount of positionality, and there's also some amount of the fact that we're way zoomed in here, right?
Yeah, yeah.
I'll
I
always
guess that's
be
true.
you can make any device look good or look bad based on the scaling of the graph.
Yeah, that's much better.
But there's also some positional issues. As I said, unfortunately, I do not have the ideal test setup here. Now, real quick, let me just show you one last measurement. I'm going to go to transfer function. So I love sine waves. I test with sine waves all day long. At home, I turn on my hi-fi and I just listen to a 1 kilohertz sine wave until I fall asleep. But most of the rest of humanity doesn't do that. And one issue that we're running into is we're embedding microphones in devices like phones and smart speakers that have active signal processing and are going to treat sine waves as an undesirable noise that is to be canceled. So one thing that's handy is to use a transfer function measurement where we're really going to just compare two arbitrary signals. And the beauty of that is that signal could just be human speech. And that's great because that is going to get carried through our device under test. So now I'm going to go and select, I happen to have some proper IEEE real speech signals. And let's and now the settings here are a little bit complicated, but the question is, what is the thing that we're going to calculate our transfer function against? And exactly here, instead of calculating it against the generator, I'm going to calculate it against an input channel. And that input channel could be one of the inputs on PDM16, or it could be my reference microphone. The match is a bit of if we were doing an asynchronous test, we're not, so I can actually just set that to none. The time alignment is if I want to take out any time of flight, and I will say, yep, I want to align that relative to the reference, or I don't want to do any time alignment at all, or I'd like to time align it relative to one of my input channels. And I'll say, yeah, I want to look at the time alignment of the channels on the board itself. So I'll do the time alignment vis-a-vis PDM16, and I'm actually going to do it to channel 2 because that's the one that's closest to the speaker. And let's do this at 48,000 sample FFT transform. And we're going to do a bunch of averages with some overlap because human speech has a lot of silence in it, actually. And I'll do it until I have averages equal to the length of my stimulus signal, which is 10 seconds. There we go. And then I'll say go. Oh, analog input range changed. Thank you. I'll fix my input range.
Dan, can we hear that signal too?
I'm happy to send you the WAV file. I'm not currently technically set up to route the audio from the APX into this Zoom meeting.
Okay.
Okay, so actually the first thing that I look at when I look at the outputs of a transfer function is what's called the coherence. And the coherence is kind of what the word suggests. It's like how closely does the output of the device under test match the magnitude and phase of the input to it. And so the range is 0 to 1, or you can have it in percent if you want, but most people look at coherence as 0 to 1. And what you can see is as the energy output of both the signal and the speaker falls off, our coherence falls off at high frequency, and it also has some problems at low frequency. But again, in this range, and this is a speech signal of like 100 hertz to 10 kilohertz, our coherence is pretty great. So that's kind of the range in which we're going to look for comparison of results. And if we look at FRF magnitude, so here is the frequency response. Now again, I kind of want to ignore some tails. So let's look at it in the range where we had good coherence. So here's the magnitude response within that range of the measurement. And we can look at this in dBFS per Pascal. And so here's our frequency response. And again, what's cool about this is we've gotten the frequency response without having to use a sine wave as a stimulus. Here is our phase. Now, one thing to notice is how the calculated phase gets wonky at high frequencies, and that's, again, the coherence has fallen off, and so the calculation of the phase goes sideways when there's poor signal to noise ratio, but sort of, again, in that range where we have a good measurement. Just to get the noise off the screen, we get a very nice plot of the phase response. And you do also, some signal processing guys say, hey, can I get the impulse response so I can feed that into a filter generation algorithm? If you're curious, here's the actual acquired signal from all 16 mics.
Can you explain how the overlapping averages works and what the reason for that is?
Sure. It's almost as if I've queued you up with questions, Jeff. So here's our actual.
I should know the answer, but I'm asking, truthfully.
Yeah. So here is the actual waveform, and this is I should have set this up so we could actually hear it, but this is an actual human male speaking a bunch of Harvard reference sentences. And as compared to a sine wave, you notice that, if we looked at this as an amplitude envelope, there is a lot of silence in human speech, where we pause when we say things, where we modulate our amplitude. And so, whereas if this was just like a 1 kilohertz sine wave, you can sample a 1 kilohertz sine wave for a few milliseconds and have a measurement. But with human speech, because it's so variant with time, you really need to integrate over a long period of time to get a repeatable measurement. So there are two things. We could just make the FFT long enough so that we capture the whole signal, but that would, FFT calculations are exponentially increase as you increase the acquisition time. So that would be prohibitive from a computational standpoint. So instead, what we'll do is we'll do a relatively short, actually still relatively long FFT at 48K, but not millions or tens of millions of points. And what we'll do is we'll average them. So what you have to imagine is at 48K, it works out that each FFT is 1 second long. So we do an FFT from 0 to 1, and that encompasses that portion of the signal. And then we would do another FFT, and then we would average those FFTs together. The overlap comes in instead of going from 0 to 1 and then 1 to 2 and then 2 to 3, is I've set the overlap at 50%. So the second FFT is going to start at 500 milliseconds and go to 1.5 seconds. And the reason we want to do that is the FFT itself has an amplitude window, which tapers at the beginning and end of the acquisition. And that taper is excluding energy. So we're just trying to essentially slide an averaging window through this entire acquisition so that all the energy in the acquisition gets included in our calculation. And it doesn't necessarily have to be this long. So for example, we could take a look at, let's capture just 2.5 seconds. But you notice it's gone kind of wonky up here. And that's definitely, and our phase is kind of wonky. And we just haven't gotten enough, this is a signal that's varying with time. And so we're just doing averaging so that we can get as much repeatability as possible.
Oh, that makes more sense.
And I was wondering, the earlier coherence you showed, it was oscillating back and forth. Is that a function of the fact that I believe you only use a sweep time of 2.5 seconds? If I saw that earlier menu where you set the generator, could that?
No. So in this case, so if we go back to. So now I've set this so the total acquisition length for this measurement will be 10 seconds.
Okay.
And what's interesting here is we're looking at coherence, and this is between the reference microphone and the MEMS microphones. It's actually, so what's interesting is we have actually some coherence at low frequency, because what's actually going on is it's picking up the room noise, and that's essentially becoming part of the test. If I set my reference to be generator,
So the mics aren't in a box. I know they're remote and you can't see them, but they're in a
correct.
In a
They're actually
room.
they're just sitting in a table.
Okay.
So notice how our coherence has completely fallen off at low frequencies. And that's because now we're looking at the coherence between the speaker's output and the mics, and the speaker just has no output at low frequency.
Right, yeah. And you're using a Hanning weighting window when you're discussing leakage and averaging earlier?
So this is actually an equi-ripple window that I'm using right now.
Okay.
You can select your FFT window that you'd like to use.
Interesting. Is that your own invention? That's I haven't heard of that.
I would like to claim that it is. It's not.
Okay.
And we've been playing around with FFT windows for a really long time, and it's our favorite. I mean, for me personally, this is getting super obscure, but pretty much there are two windows that I use. I either use equi-ripple or I use flat top, or none. But I don't really, that's not really a window anymore.
Right.
Okay, so I've gone a bit above my time. I like to, just take a moment and entertain any questions anyone has.
The sensitivity measurement, is that specific to version 6?
Yes.
Okay.
Transfer function was added in version 5.
Yeah.
Multi-input and sensitivity was added in version 6.
What is, I don't quite get the name sensitivity. That does
I
not
know.
equate to what I think that
know.
would, that should be. That's why I didn't understand when you were talking about sensitivity. So.
I know. So the reason we called it that is the result it gives you is what most people think of as a sensitivity measurement. So this is dBFS per Pascal, and I completely agree with you. All I will offer you is that in my time doing product management, I've learned to stay out of fights involving colors or names.
Fair enough. Yeah.
And so we call this sensitivity because the result it gives you is what most people think of as sensitivity.
Now, of these two tests, this acoustic response and the transfer function, which one would you trust on a daily basis, or is that really dependent on what you're testing and what signals you're testing with?
Yeah, I mean, the thing is if I'm testing, it's pretty simple. If I'm testing a bare microphone and there's no active signal processing involved, and so I know that I can use a sine wave as the stimulus signal, then I would use acoustic response or continuous sweep or some, sort of a standard measurement. Transfer function is really handy. Well, in fact, it's pretty much your only choice as soon as you're testing something where there's active signal processing involved and you don't get to pick your stimulus signal anymore. Again, in the telecom world, for example, there are a bunch of tests where you're required to use IEEE real speech as the stimulus signal, and sort of that falls into that category where you don't get to pick your stimulus signal, and now you need to make a measurement using something other than a sinusoid.